Hey Tim, check out this chapter on modulus, which means the absolute value. Absolute value means that the sign is taken away. We're just looking at the magnitude or the size of the number, so it's always positive. So if we look at this first example, we say y equals mod x. It's the mod sign over there. And we can see that if x is bigger than 0, then y is just equal to x. But when x goes negative, our line would continue down here if you plot the y equals x straight line. And so you need to reverse the sign of x. So we say that y equals minus x, okay? Because in this area, x is always negative, so minus and minus gives you your positive. And there you have now the graph of mod x. Similarly, if we have an equation y equals mod x minus 2, we can easily plot the line, the straight line that goes down to minus 2 with a gradient of 1, and there it is. And we can see that the minute x goes below 2, the sign goes negative, and we need to invert it. So for this section, to the left of the 2, we've got y equals minus x minus 2. And above that, we just have the normal function y equals x minus 2. Sorry, that's minus x plus 2. So the whole function has to be inverted. So every term in the function gets inverted. As soon as this goes negative, we just flip him over the x-axis. You can see in both these examples how the mod graph is always above the x-axis. It's like a mirror in the x-axis. You can see that would be the function, but now it's inverted around the x-axis. And it doesn't matter how complex the function is, it's the same principle. Here's a quadratic, normally would look like that, but if we have the mod, if we want to find y equals mod x squared minus 4x plus 3, okay, then this middle part is negative. So what do? We have to put a minus in front of everything. And so the function changes from there. It's a normal function, x squared minus 4x plus 3. From here, it becomes minus x squared plus 4x minus 3, and then it reverts back to the original function again. Okay, so if we want to plot a function like this where we have a combination of two mod terms in it. So we're saying y equals mod x minus 2 plus mod x minus 1. We need to look at these critical points, and that is where x equals 2 and where x equals 1. Because at these points, this is where y is touching, or rather this function x minus 1 is touching the x-axis. And so we expect there's going to be a flipping around the x-axis. So if we look for x is above 2, the term x minus 2 is always going to be positive. So that portion will just revert to x minus 2. We can take the mod sign away because it's always above, it's always positive. Similarly, the x minus 1 is also positive. So the function above for x above 2 is going to be the sum of x minus 2 plus x minus 1. And it's pretty straightforward. It's 2x minus 3. Now if we look at the area between 1 and 2, the x minus 2 term is now going to become negative. So we need to flip him, because let's say x is 1.5. You'd have 1.5 minus 2, which is negative. So anything between 1 and 2 is going to be negative. So you need to change the sign. So instead of the x minus 2, we change that function to 2 minus x. And the x minus 1 is still positive. Because say x is 1.5, it's 1.5 minus 1, it's still positive. So x minus 1 remains. Now we're going to add the 2 again. But now we're adding 2 minus x plus x minus 1, which just gives you a 1. And then finally in this zone, the 2 minus x remains because the x is going negative now, so that's always negative, so we need to flip him. So it's 2 minus x, and the x minus 1 also flips. Now when you add those two terms together, you get the 3 minus 2x. Now each of these functions, 3 minus 2x, which applies to this zone, and just the number 1 applies to this zone, and then 2x minus 3 applies to anything above that. So you can see this is how the graph gets plotted. So it's basically a composite function now made up of these equations. They get added together, and you have three different functions that make up plotting the graph. So it's important to identify these critical points where one of the components in your mod equation is changing sign, where the y is going from positive to negative. And if you stick to that rule, it's pretty straightforward throughout. Okay, so here's another fun example. Y equals mod of mod x minus 2. That's an interesting one. You've got a mod within a mod. So if we look at the mod x, that gives a critical point at x equals 0. So if we say, okay, let's treat that, we draw a line in the middle there, and we look at everything on the left and then everything on the right, where x is above 0, where x is below 0. If x is below 0, then mod x becomes minus x. So now we've got y equals mod of minus x minus 2. If x is above 0, it just remains x. So y equals x minus 2. So we've got rid of one of the inner mod sign already. But now we've got to remember this equation only applies where x is smaller than 0, and this one only applies where x is bigger than 0. If we look further, let's take this one. You see there's a critical point at x equals 2. And therefore, when x is smaller than 2, then the equation becomes minus x plus 2, because it's negative. Okay? So for example, if x was 1, you'd have 1 minus 2, it's negative. So you need to reverse the whole function. And if x is bigger than 2, it remains. So if it's bigger than 2, then that's going to be positive. So your equation doesn't change. You just remove the mod signs. So now here's another 2 zones. That's been this zone has been split into 2 more zones. And similarly, same applies on the where x is smaller than 0. Okay, yeah, looking at this equation, we've got a critical point at x equals 2. No, x equals minus 2. Sorry, minus 2. Minus 2. And that gives you 0. So your critical point is at minus 2. And for this zone, we say, okay, there's our critical point at minus 2. And when x is very big negative, you can see that's positive, so that, because it's minus minus, becomes very big positive. So you can just remove the mod sign, because that is positive. Then, say if x is minus 1, you're going to get a negative number. So you need to invert him. So both the minus x becomes an x, and the minus 2 becomes a 2. Both signs have to be changed. It's very important to remember that you must change the signs of the entire function. You're not just changing the sign of x within the mod. You're changing everything inside. So here are my 4 zones now. I've got 4 equations. Y equals minus x minus 2, y equals x plus 2, y equals minus x plus 2, and y equals x minus 2. Each of these zones now, you can draw them quite simply. So we can just say, right, well, this one, he's got a c value of 2, and he's going down at 45 degrees, so he goes down to 2. Well, this one, he's on a line that cuts at minus 2 here, but he only applies from here, so he does that. Okay, there's a nice positive slope there. And similarly, you'll see this one will draw that, and that will draw that. And that's how we draw our graph. Okay, that'll be, that's 2, that's number 2, that's 2, that's minus 2. And that's how we plot him. If we get given, let's have a look at an example like this. If we get given an example like this, mod x minus 2 equals mod 2x minus 1, we could sketch this in a similar manner in which we've sketched the previous ones, and we could find the coordinate where these two lines meet. Or alternatively, we can also say, let's make if x minus 2 is, can remain positive, and it's equal to 2x minus 1, or x minus 2 could be minus 2x minus 1. And that gives us 2 solutions of x equals minus 1 or 1. So there's only the signs can be reversed. If the one is positive, the other one's negative. The other one is positive, the other one is positive. Okay, so there's only 2 combinations. You might think at first glance there's 4 combinations, but actually there's only the 2 combinations. Because having a minus and a minus is the same as a plus equaling a plus, and having a minus equal a plus is equal to a plus equal a minus. So you only need to do it with the 2 tests. You can pick the first one to be positive always, and the second one to alternate between positive and negative. We can now look at how to solve inequalities with equations that have moduli in them. For example, here's modulus of x minus 2 is bigger than or equal to modulus of 2x minus 3. So first of all, let's do the graphical method. If we look at the first one, we see that x minus 2, mod of x minus 2, has a critical point at x equals 2. So there we have them there. And we can draw the graph. You can see above 2, y equals x minus 2, and below 2, y equals minus x plus 2. The whole function inverts. And similarly, we can plot y equals mod of 2x minus 3. There we can see the 0 point is at 1.5. Now, if we look at this, we see, well, where is x minus 2 bigger than 2x minus 3? And the 2 meet over here, and over here, and there we can see the mod x minus 2 is bigger in this interval here. And you can read that off a graph, and you can see x is between those two numbers from 1 to just less than 2. So that's one way of doing it, using the graphical method. I must confess it's not my favorite method. You have to read things off a graph and you don't always get the right value. Here's another way. So first of all, we're going to identify the critical points. We already said that the first point is 1.5. Okay, that's the critical point for the mod 2x minus 3. Now we don't need to draw this graph. We just need to know our critical point is at 2x minus 3 for the first one, and at x equals 2. Now we have 3 zones here. We have everything above 2. When everything's above 2, the functions revert to x minus 2. There's no change, so you just take the mods away because x is big, and also the 2x minus 3, also no change. Now you just need to say x minus 2 is bigger than or equal to 2x minus 3. And just rearranging the terms, you can see that x must be smaller than 1. Now this is where it gets important. This equation only applies when x is bigger than 2. So if x is smaller than 1, there are no x's that satisfy the condition. So there's nothing that comes out of this. We ignore that section. Let's look at the next zone, between 1.5 and 2. Okay, that's all we're looking at. If we look there, we see that the x minus 2, because it's less than 2, the x minus 2 must flip, and it becomes now 2 minus x, which is bigger than or equal to the 2x minus 3 is still bigger than 0, so it remains as it is. The function doesn't change. So now I have 2 minus x is bigger than or equal to 2x minus 3, and rearranging the terms gives us x is smaller than or equal to 5 over 3. Now 5 over 3 is in the zone. It's about over here. Okay, so it means that for this condition to be satisfied, x can be anything from here to here, because we only can work within the zone. So it's from the limit, from the edge of the zone to 5 over 3. Now let's look at the last zone. Here we have the x minus 2. The mod of x minus 2 has already become 2 minus x, and now the 2x minus 3 becomes minus 2x plus 3. Now, because it's now also negative, they're both now both signs have changed on them. So now we have, rearranging the terms, we say that x is greater than or equal to 1. Okay, so 1 is within my zone. There's 1, and x must be bigger than that. So the final answer, x must be bigger than 1, but smaller than 5 over 3. And that's, so in these two zones we were able to get some joy, but in this one we had to disregard any answers. It's just so important to remember that the functions are different for each of the zones, but the functions only apply within their zone. So always bear that in mind. And there's no need to plot the graph. You just need to put it on a number line and say, right, number 1, where are my critical points? That's crucial. And then how do the functions change? It's also worth remembering the functions only change, each function, subfunction, only changes once. So you don't need to calculate in each zone. So if we take the x minus 2, the critical point is at x equals 2. So above that it stays x minus 2, and below that it becomes 2 minus x for both of the other zones. Okay, similarly, the 2x minus 3 only flips at 1.5. Okay, so above that it remains 2x minus 3, and below that it becomes minus 2x plus 3. So you don't need to work out each one 3 times. You only need to work it out once. You can fill it in on each of the zones, and then you've got your new equation for each zone. Okay, I'd like to just discuss, as an aside, how to draw polynomials quickly. In AS Maths, often you need to be able to know what the graph's going to look like before you go into some detail. And yeah, there's a couple of simple tricks or things one can memorize that might help, able to draw a line quickly so you can see where it is, even if you're integrating or if you're trying to find the modulus, just to have an understanding of the shape of the graph. Obviously, a linear graph is very easy. We can say y equals mx plus c. So for example, if we have y equals 3x plus 2, first thing you need to look for, you draw your graph, you look for your c value, it's on 2. Okay, that's where it cuts the y-axis. When x is 0, the 3x falls away and you're left with 2. Then you look at the slope. You can say, right, it's going upwards because the slope a value is 3, it's positive. So it's going to look something like that. So it's very easy to find pick any coordinate, maybe x equals 2, you put it in and you'll find that you're going to be plotting it against the number 8. And so it goes. So a linear is quite simple. What I want to point out though is that the index, the power of x is 1, it's odd. And so we have the slope. Okay, there's a it's either falling from left to right or rising, but it's odd. It's your first odd power. If we look at a quadratic, it's an even power, and it's going to be like this, depending on a. Okay, if a is positive, you're happy. If a is negative, you're sad. And that's how it goes. So that immediately tells you how your graph's going to look, which direction it's going to be, up or down. And then there's 4 key points that you can find to quickly draw a graph. First of all, your c value. So in this case, we've got y equals x squared minus 3x plus 2. We can see that it cuts at 2. So there we go. We've got our first point already. Now, you would normally have to find the roots here. But in a lot of examples, maybe they give you the roots. They write y as x minus 1, x minus 2. For heaven's sake, don't times them out because you're wasting time here. You need to look at that immediately and say, hang on, they've given me the roots. The roots are at 1 and 2 because that's where y is 0. So we write in there 1 and 2. So we already have 3 points to draw a rough sketch of our graph. And if you want to go into more detail, you could say, right, the min-max x is equal to minus b over 2a. So you can quickly calculate that and you'll find out it's somewhere there. It'll always be between the 2 roots exactly. And now you can draw your graph. Okay, quite easily done. And that'll give you an idea. So yeah, from there you could now say, okay, I need to find the mod of this, so you can know exactly where your critical points are. That's where the quadratic is 0. Similarly, with a cubic function, it's another odd power. So what do you expect it's going to be? It's going to be high and low. Okay. Now, that was straight line. This is x to the 3, x to the 5. It's going to get tighter. The elbow will get tighter, but it will effectively be the same shape. And similarly, with your x squared, there we go. We've got an x squared. Then you've got an x to the 4 and an x to the 6. It's going to get tighter shoulders and steeper. And that's the difference in these curves. It's important to be able to draw them quickly. Okay, so let's look at this little guy, a cubic. Okay, it looks very daunting. So it's an odd power. So we know that when x gets big, it's going to be going up there somewhere. When x is small, it's going to be going down there. Okay, that's because a is positive. There you can see when you times the x's out, you're getting a positive 1 as a. X times x times x. That's your x3 coefficient is 1. Positive. So it's increasing from left to right. Now again, they've given you the roots. Don't times this boy out because it's going to take you a long time and you're going to make mistakes. Okay, and it's not going to help you because then you've got to find your roots again. So we can see their roots here at minus 1, at 2, and at 4. So very quickly we've got an idea what this guy's going to look like. We're not going to find the min-max. You could easily find it using differentiation. and finding stationary points. But you can see, if you're coming from here, you need to pass through that point there. Then it's going to go high. In fact, you've got your C point as well, which would be at 1 times minus 2 times minus 4 is plus 8. So it's cutting at 8 there. Okay, and then he's going to go up, go down. He's got to carry on because it's a continuous graph. So he's going to go up there. And there you go. Now you've got a nice sketch of your x to the 3. If they wanted to see what mod of x of this function is going to look like, well, you know what it's going to look like. It's going to be reflected in the x-axis. And there you go. Okay, so it's quick to draw. So what are the mod properties? First of all, for multiplication and division. Okay, you're not going to read this very well, but if I've got mod of a times b, it's equal to mod of a times mod of b. Okay, I hope you can read that. And similarly, mod of a over b equals mod of a over mod of b. So that's one of the rules. Please, this does not apply to addition and subtraction. Okay, if mod of a plus mod of b is not equal to mod a plus b, because a and b could have opposite sides. They could be fighting each other, but when you add them, they're going to be big. Okay, so remember that addition does not apply, multiplication and division does apply. And then there's a term called modulus notation. Okay, and this is important to know because you're going to get questioned on it. So modulus in measurement is applied when we measure things to correct to say 2 decimal places. So modulus notation means when you write it in the form x minus k is smaller than or equal to a. And that's the same as saying k minus a, or x is between k minus a and k plus a. And it's important to remember that a has to be positive for this to imply. So what are they talking about? Let's do a little example. If, okay, so switching between the two formats. For example, if a length is measured as 87 centimeters, correct to 2 significant figures. Note the wording, 2 significant figures, not 2 decimal points. What is the range of the actual length in modulus notation? So this guy's measured something to 87 centimeters, but what is its actual value? Well, the lowest actual value could be 86.5, and it could go as high as 87.5. So k in this notation is actually the midpoint between the two extremes. So if we take the k would be then 87. Okay, it's actually the measured value that's been rounded off. And so x minus 87 must fall within 0.5. Okay, because 0.5 is the threshold for the 2 significant figures. So I hope that helps to explain how it works. Then just be careful with the wording. So that question was with 2 significant figures. If I'd asked to 2 decimal points, it would have a completely different meaning. Okay, so now the x has been measured to 87 centimeters, corrected 2 decimal points. It means the highest value could have been 87,005, before it clicks over and rounds to 87,001. Okay, so the highest you can go is 87,005. The lowest is 86,995. So what's the error? You can see it's 0,005. So your a value is 0,005 now. Okay, your median between the two is still 87. So you'll write it as x minus k, which is your midpoint. Your 87 is smaller than or equal to the distance from the midpoint to one of the extremities, which is 0,005. So it's quite easy to find these values, but one needs to have an understanding of where the a value comes from, which is from the halfway to either one of the extremities, and the k value, which is the midpoint. Okay, then finally with the modulus, one can use squares as well to find either inequalities or equals. So if mod a is equal to mod b, it follows that a squared equals b squared, because mod a is positive, mod b is positive, and if you square them and they're equal, it makes sense that the squares would also be equal. So if I took an example like this, where mod x minus 2 equals mod 2x minus 1, and square both sides, I get a quadratic on the left-hand side, a quadratic on the right-hand side, and if I rearrange these and take out the factors, or find the roots of it, I'll find that x equals 1 or minus 1, and you can do that exercise. It's quite a simple one. And here's another example where you have mod x minus 2 is greater than or equal to mod 2x minus 3. That means if I square this side, it will also be greater than if I square that side, since both of them are positive. And so you get x minus 2 squared is greater than or equal to 2x minus 3 squared, and it follows then that you end up with a quadratic 3x squared minus 8x plus 5 is smaller than or equal to 0, and from there we can factorize it. Okay, this does not mean that x is equal to 5 over 3 or x equals 1, because it's an inequality. Just be careful of that. So for this expression to be smaller than 0, it means that either this one must be plus and this one must be minus, or this one must be minus and this one must be plus. So let's take the first case. We take the 3x minus 5 is positive. So 3x minus 5 is greater than 0, and x minus 1 is smaller than 0. Then that following from here, x is greater than or equal to 5 over 3, and x must be smaller than 1. Okay, is that possible? Not really, because x cannot be bigger than 5 over 3 and at the same time smaller than 1. So that has no meaning. This solution has no meaning. If we look at the other option of making 3x minus 5 negative and x minus 1 positive, then we have 3x minus 5 is smaller than 0 and x minus 1 is bigger than 0. That leads us to, from here, x is smaller than 5 over 3 and x is bigger than 1. And that's entirely possible. So x can be anywhere between 1 and 5 over 3. There you go. X is in the range 1 and 5 over 3. Now just a tip, you can only use this trick of squaring both sides when you have positive mods. Don't dabble in squaring expressions with, for example, a minus in front of one of the mods. Because often, well, usually this will mean that there is no answer, because once you square, a negative mod cannot equal a positive mod, because a negative mod is always negative and a positive will always be positive. So you square them at your peril. So if you see a minus in front of there, beware. Rather do another approach in trying to solve for x. Okay, thank you very much. Ciao.